Hello students, welcome back for lecture series. So today's topic for our discussion is design of belt conveyor. So quickly we will take a review on the design pages which we needed for a belt design conveyor. So from PHG page 9.18 onwards, we require those pages for our belt conveyor design. So you are on the screen. You might be seeing PHG page number 9.18, where few equations, standard equation regarding to their belt resistance on top run and bottom run are given, plus different tension formulas are given over there. Then how to calculate the belt thickness, transmission ratio. These equations are shown over there. Then few standard information related to uh, weight of idlers, weight of conveyor size, then density. Based on the density of conveyor, how we can choose the maximum spacing in between idlers, then allowable belt conveyor speeds based on the type of material which to be conveyed, the number of plies for belt design purpose, then tension in a belt conveyor based on the type of design, belt design, or you can say a type of belt manufacturing concept. We can find out the designation of the belt from table number 5. Then density of an angle of response, or you can say angle of inclination, is given for a particular material, standard materials. Then bucket type of belt conveyor, if you want to design, you can refer this page number 9.23. So the parameters of bucket levers are uh, sorted out over there with the range. Okay, so then design of screw conveyor, which is on PHP page number 9.26. Design of pneumatic conveyor, that is 9.27. Okay, so that's all till 9.29. All major type of conveyor systems are get covered. So out of this, we are going to learn how to design a belt conveyor. Okay, so let's see. We'll go with the problem. Okay, so initially whenever you are starting your design, you must have to draw a belt conveyor system. So what are the main components that we have already discussed in our theory lecture? You may have to draw driving pulley, driven pulley. Also you have to show which is the driving pulley, because it might be a single drive system or dual drive system, so you have to show it properly. The angle of wrap, angle of inclination, troughing idlers, or whichever the top run, bottom run. If you are using any take-up system to maintain the tension between two pulleys, you have to show that arrangement also. So it gives an particular uh, idea how or what type of conveyor system, or how the generalized layout of the conveyor system is to be drawn. Okay, so this is a first step for you. while solving the any kind of belt conveyor problem. So let's see with the problem. In the problem, few specification is given. Design of belt conveyor for following specification. Material to be handled is a gypsum stone. Grain type is a non-standard because these stones are not in a particular shape, so that's why the grain size or grain type is non-standard. Working capacity 125 ton per hour. Length of conveyor is 100 mm. Inclination with the horizontal is 10 degree and the lump size is 60 mm. Okay, so before design we need to draw a layout, which is we done already. Now we have to take some general assumptions so that we can design it properly. So I have listed out four general assumptions which we are considering while design. The take-up system is given to the lower pulley so that the tension between these two pulleys get properly maintained. Single pulley driven system. So the top pulley is the driver pulley, and that pulley is only having a motor. So single pulley driven system. Angle of lap is increased by using snap pulley. If you look at over here, just a minute. Over here, this is a driving pulley. Now this is an angle of wrap. Now how we can increase by using this snub pulley. Okay, if you move upward, the angle of wrap get increased. Okay, so everybody please understood it properly and remember it. Okay, troughing angle is 20 degree. As we are using gypsum stone, there is a possibility that these stones are get fall down or moving away from the belt conveyor system. So we are not using a flat belt drive, we are using trough type of belt conveyor system. Okay, so first one, to determine the width of snub pulley, referring page number 9.18, equation is given. Let's see the PhD page. I'm just enlarging this one. Okay, here the equation is given. B minimum is equal to 1.11 into bracket Q divided by CV raised to half plus 0.05. Okay, where what is Q? Q is the conveying capacity 10 per hour. C is the factor for type of idler, and small v is the belt velocity. Okay, now that belt velocity we can calculate from PhD page number 9.20, table number 3. Okay, let's see factor for the idler. Now we are using troughing idler with the angle of 20 degree. So value of C is 460. If you increase the troughing angle, the values get increased. So standard values are 20, 25 and 30 degree. Then calculating the value of V, 9.20 here. Basically, if you consider any material, the standard velocities are given. So here we are using gypsum stone. Okay, so it is my put into this category. So initially variation in velocities are 1.5 to 2.75. Okay, so we will assume it at initial stage so that we can get a temporary, or you can see a basic idea what should be the width. Okay, so just initially note down the basic information. Q, the capacity, uh, that is 125 ton per hour. Rho is the density, that is 1.2 to 1.4 tons. Referring PhD page number 9.22. Then C is equal to factor for idler, which is we have seen that is 460 for tripping angle 20 degree, and the velocity. As I say, the range is in between 1.5 to 2.75. We have to assume. So the initial velocity we can assume is for minimum. Okay. So as the speed increases, the belt width get increases. So we will start assuming with the lowest velocity. So assume v is equal to 1.5. Now put all the data in this equation. What we get, b is equal to 0.4698 meter. Okay, so when we see the variation, or you can say standard value of the belt conveyor, that is a 500. Okay, and for 500 the velocity is 1.75. So let's see what is the actual velocity. So the standard value of belt is 500. You have consider that standard value. B is equal to 500 from page number 9.20. Now we have to make a reverse calculation so that we can find out the actual velocity inside the conveyor system. Okay, so permissible velocity, that is we have seen, that is a 1.75. Now value of b is put inside and remaining values are putting. What we get, the actual velocity is 1.308 meter per second, and which is less than the maximum allowable velocity or permissible value of the speed for 500 mm belt of that particular application. Okay, so our design is safe. Okay, here also we can write, if your actual velocity is lesser than the maximum velocity, our design is safe. Now next step, to determine the motor power. Now to drive the belt conveyor we need a motor, and now for the motor, how much power or what is the capacity or how much kilowatt, how much HP, that we have to decide. Okay, so let's see, we will discuss how we can design a motor details. So first of all, for that we need a particular things to be considered. While a driving mechanism, there are few resistance occurred. So initially rollers are mounted or belt is wrapped over the roller. So to transmit or to move forward, uh, if belt want to move forward, it has to be resist the few resistance which is occurred by the, or which is offered by the idlers. So initially we need to calculate the resistance of belt on both run side, top run side as well as bottom run side. So start with the calculating the resistance of belt on the top run side, which is denoted by W suffix O. So W is CFL into bracket GG plus GB cos of delta plus GRO plus minus HGG plus GB. Now it is very important to first of all identify uh, equation from PSG. So referring PSG page number 1.18. Okay, so you can find the equation over here. Okay, so this is a standard equation. which is given. Okay, so what is WO? That is the resistance of the belt on the top run, which is in kgf. It is written over here. C, secondary resistance factor from figure number from figure page number 9.20. Okay, we can find out that also. F is the friction between idler and belt. Okay, we can select from these three aspects: non-portable conveyor with the good idlers, standard conveyor, and idlers in a rusty environment. So based on the application, you can choose value of F. As the stones are there, the dusty environment is there. So we will choose from this last one. Length, conveyor length, you can see from figure from PHG page number 9.20. GG, the weight of conveyed material per meter length, kgf per meter. GB is the weight of belt per meter length, which is in kgf per meter in table number 1, page number 9.19. Delta is the angle of inclination of the conveyor. GRO, weight of troughing idler on the top run per meter length, kgf in meter, which is we can find out from table number 2, page number 9.19. GRU, the weight of straight idler on the bottom run and per meter length. Okay, which is our, again we can see from table number 2, page number 9.19. Okay, so these are the sorry, one parameter is missing, that is h, height of height through which the material is get to be conveyed. It is in a meter. Okay, so let's see the standard component or standard parameters we calculated. So first of all, value of C, that is a secondary resistance factor, which is considered as 1.7 for length of 100 meter, the distance to be conveyed, referring page number 1.8. Then fraction F is equal to friction between idler and belt. As the gypsum stones are there, the environmental condition is dusty. So we have considered dusty environmental condition for idler, and F is equal to 0.025. About the length to be conveyed, that is 100 meter. GG, that is the weight of conveyed material per meter length, which is in a kgf. Now we have converted into that form. GG is equal to this total material weight to be 100, that is a q capacity, divided by velocity. Okay, the capacity is given into ton per second and velocity is given in meter per second. So we are conveying that ton into kgf, or you can say sorry, ton per hour. So 125 divided by 3600, so that we can get a particular parameter, a particular value, divided by velocity. Actual velocity is 1.3.0603. So we get the total value is 0.0266 ton per meter. Okay. Now multiplied by 1000, you get value of G is equal to 26.6 kgf per meter. Okay, so you must have to understood this thing conversion properly, because most of the students are get confused while designing, and they do some wrong calculations in this part. So everyone please take care while calculating the value of GG. Next one, the value of GB, that is a weight of belt per meter length, referring page number 9.19, table number 1. Okay, let's see. So now table number PhD page number 9.19, table number 1. You can refer this table. Belt width, that is a 500. The average weight per meter run is 6.5 kgf. Then value of GRO, the weight of the troughing idler on the top run. Okay, referring PhD page number 9.19, table number 2. Okay. Okay, to calculate the value of GRO, we have to make some assumptions. Okay, look at the table number 2. Refer this table. Okay, so while selecting the idler, first of all, we need to find out the tube diameter and the belt bearing diameter, because we have only a belt diameter, or we can say belt width, that is a 500. Now there are two types of idler spacing over here, that is a troughing idler and straight idler. For top run we are using troughing idler, and for bottom run we are using straight idler. Okay, so for and maximum weight which is carried on top run only, so we will design based on the troughing idler. Okay, so for 500 mm, so for 500 mm, the value of two diameters available are 100 and 125, and anti-friction bearing which is used over there are 20 and 25. So out of this we are selecting this one, that is a tube diameter is 125 and belt diameter bearing diameter is 20. Let's just see what we have written in our design. Okay, tube diameter is 125, bearing diameter is 25. So the value of the weight of troughing idler is 20 kg per idler's assembly. Okay, you can look at over here. So this is the value. Okay, so once again I will repeat. Initially we have only belt width in our hand. Okay, so first of all track the belt width, and second thing you have to choose, we have only belt width. Now we have to choose from here troughing idler or straight idler. So out of that I'm choosing troughing idler because I'm designing a top run where the maximum load is get carried out. Now we have a belt width, so I'm marking the belt width row. So in a belt width row, now I have to choose a tube diameter and the bearing diameter. So available capacities of those are crossed over here. That is, a tube diameter is available first 100 or 125. I'm going for maximum, so I'm selecting 125. Now with same tube diameter, there are two bearings are available. 20 mm and 25. I go with the maximum 25. So the value for these, what we get, the value of troughing idler or weight of troughing idler per uh, per assembly, which is 20 kg per idler assembly. Okay, I hope everybody get properly understood it. Okay, now angle of inclination delta is given, that is a 10 degree. The density of the material is 1.3 ton per meter cube. The maximum spacing between the idlers. Now we have to refer table number 3. So the maximum spacing we can find out. So for maximum spacing, again we need to check the belt width as well as the density of the material. Okay, so for return idler, the values are given here, and for top idlers, the values are given over. So we are referring 500 value. Sorry, belt width is a 500. Our density is 1.3. Density is 1.3. So it is lies in between this segment. Okay, so the value you can find out is 1.5 meter. Now we have to calculate the height of the height on which or through which the material is to be conveyed. So we have a vertical or you can say a horizontal distance and angle of inclination. So here h is equal to L sine of delta. L is 100 multiplied by sine of 10. So what we get, the height h is equal to 17.365 meter. Now we have to add a plus sign while calculating the value of W0, putting all the values into the equation, in this equation, and here we have to make a note that here you have to use a positive sign only, because the material is going to be conveyed conveying in a upward direction. So material is going to conveying upward direction. You have to select the sign positive sign. Okay, so W0, after the calculating, what we get, W0 is equal to 762.1679 kgf. Okay, now similarly we need to calculate the resistance of belt on bottom run. Okay, so few things are would be the same one. Now only the thing we need to change the value of GRU. Okay, so we need to select a negative sign for calculating purpose. From this equation, if you look at this equation, the value of CFL, then GB, HGB, which is already we have calculated. Only we need to calculate value of GRU, and we in this equation we need to select a sign from positive or negative. We have to select negative sign because we are conveying a material in upward direction. Okay, now let's see how to calculate the value of GRU. So GRU is the weight of straight idler per unit length. Okay, as per from PhD page number 9.19, as we selected from table number 2, as we selected the troughing idler for top run, for bottom run we need to select a straight idler. In similar fashion which we selected previously, we can select, uh, we have a belt width of 500 mm, then the 125 tube size, then 25 mm bearing size. So value of GRU get 10.7. Okay, 7.7 kgf per idler assembly. Now the spacing between a return idler, which we have seen from table number 3. Uh, okay, here it is a standard value, that is a 3. Number of spacings is given for all the variation in the belt width. So we have selected these 3. Okay, now putting all the values in the equation, you get the value of sorry, uh, spacing between idler is 3 spacing. Now how to calculate the value of GRU? GRU is nothing but the weight of idler per assembly. Okay, so weight of idler we calculated, that is 10.7, and the spacing between idlers are 3. So there are 3 idlers we are selecting. So for each idler, the value of GRU, the weight of straight idler per meter length, that is equal to 10.7 divided by 3, that is 3.5667 kg per meter. Now putting this value of GRU in WU, we get the value of W is minus 72.2019 kgf. Now net pull action on the belt drive, that is the power. Okay, so the P is equal to W0 plus WU, referring page number 9.18. This equation is given in a PhD. So P is equal to W0, that is 762.79, plus WU, that is a minus 72.2019. So actual net pull action or net pulling action, or that what you can say load or force which is acting by the belt drive, that P is equal to 619.597 kgf. Now we need to calculate a power for a drive. So equation is given, power in HP, P is equal to, sorry, power is equal to net pull action into the velocity divided by 75 into NP, NPR, and efficiency of transmission. So the transmission efficiency we have considered 96%. Pulley efficiency, as it is operating on the pulley. So these are mechanical components we have to consider. So pulley efficiency is considered 95%, and the bearing efficiency, which is considered as a 99%. So putting all the values, what we get, the power in HP is equal to 13.299 kilo. Okay, so it is in a horsepower. Now we have to convert this horsepower into the um, kilowatt, so that we can we can select the standard motor size. Okay, so to convert that, we need to multiply the value of HP into 746. What we get, uh, the motor power in kilowatt is equal to 9.917. Okay, sorry, it is divided by 747. So we get actual motor capacity, that is 9.917 kilowatt. Referring page number 5.125. The standard motor is you can use a flange mounted 3-phase motor with a speed of 1500 rpm, and the motor rating, standard motor rating is 11 kilowatt. Okay, so in this way we can calculate the design motor or select motor for belt conveyor. Okay, so in this lecture we will cover up that much. In next lecture we will discuss the remaining design. If anyone having any problem while designing, you can free feel to call me. Okay, so thank you very much. In this next lecture we will discuss the remaining design appropriately. Okay, thank you.